Hello, this is Mr. Gilmore with the 2.1 Conditional Statements lesson. In this class, we are going to be proving theorems, and every theorem that we encounter is going to be what's known as a conditional statement. And so we're going to learn the importance of what a conditional statement is, but before we get to the definition of conditional statement, let's start with the definition of a theorem. A theorem is a statement that has been proven true. So unlike definitions and postulates come to us as being true. Theorems must be proven true. And once we've proven a theorem to be true, we can use it just like we've been using our definitions and postulates. A conditional statement is a statement in the form if blank, comma, then blank. We will fill in those blanks with a statement for each of those blanks. So, for example, if we have a conditional down below, we can say if two angles are vertical, then they have the same measure. So it's very much like you've seen conditional statements in the past. Like so, for example, if you don't clean your room, then you cannot go out and hang out with your friends. So there's conditional statements made such as this in geometry, where we're going to say if, and we'll fill in that blank with a statement, then followed by a conclusion to that statement. We will fill in for a generic conditional the words given and conclusion. So if I was talking about just some conditional form, I would say if given. So the given is what we are starting with, comma then conclusion. That's the statement we want to reach, and we're going to see that's how our theorems are formed too. We'll say if given, comma then conclusion. Now, not all statements are in the form of an if-then statement. We call these implicit conditionals if they're not in that form. For example, below we see a sentence that says, I think, therefore I am. Note that you don't see the word if, or you don't see the word then. But we can change a statement such as I think, therefore I am into a explicit conditional, which is the if then form. And we would find then we can just insert our words if and then. Now you may have to change the grammar around a little bit so that it still makes sense. So I would read that as if I think, comma, then I am. Let's practice that. So we have a statement here. Vertical angles share their vertices in common. Alrighty, vertical angles share their vertices in common. I don't see the word if, I don't see the word then, but I could change this into an if-then statement. Let's try this. Now, when I do this, I'm going to have to change some of the vocabulary words around so that my sentence reads well. Let's try this. If two angles are vertical, now note again, I had to grammatically change my sentence around, then they share their vertices in common. And there we have it, right? Taking our implicit conditional form and turning it into an explicit sentence with the if-then statement. Let's do another. Primes greater than 2 are odd. Okay, so if a prime is greater than 2, then it is odd. Didn't have to do too much of my grammatical restructuring there, but you do want to make sure the sentence reads well. You can't just chuck the if and the word then in there and expect it to sound well when you write it out. Now, not all conditional statements that we encounter will be true. Now, most of the ones we do encounter will be true. But if we find a conditional statement that has what's known as a counterexample, we then find this conditional statement to be false. As what we'll see here in a moment, a counterexample proves that a statement is in fact false. Now, what will a counterexample look like? It could be a number of things. It could be an actual number. It could be a word, a term, such as a definition. It could be a postulate, and even it could be a theorem that would prove that conditional statement wrong. In other cases, it may be a figure. You may draw a diagram that actually is a counterexample to the conditional statement. Here's an example of a false conditional statement. In the middle, we read, if a number is prime, then it is odd. If a number is prime, then it is odd. There is a counterexample to the statement. The counterexample is the number 2. Now note that the number 2 does in fact satisfy the given, and that must be required for all counterexamples. It must satisfy the given. Then, in order to make this conditional false, it has to fail the conclusion. And look, 2 is not an odd number, so it satisfies the given, but it fails in the conclusion. That's what we're looking for in a counterexample. So the only way to make a conditional statement false is to make sure that the given is true, make sure the given is satisfied, and the conclusion is false. That's where we're going to find that it fails in the conclusion. Let's do an example. If two angles are adjacent, then they form a linear pair. Well, we're going to analyze this statement and we're going to determine maybe I could have two angles that are adjacent and then they form a linear pair. Let's see if this is true or false. And if it's false, we're going to provide a counterexample. Okay, so I'm thinking in terms of adjacent angles, right? Adjacent angles have a common side and their interiors do not overlap. Well, as I think about this, this statement is actually false. I can think of plenty of adjacent angles that don't form linear pairs. For example, I could have this be my adjacent angles. Notice that their non-common sides do not form a line. That would be the part of a definition of linear pair. So this is false, and I use the diagram here as a counterexample to the statement. Just as stated before, counterexamples could be anything: numbers, words, terms, even figures. How about another example? If a figure is a polygon, then it is composed of line segments. All right, if a figure is a polygon, then it's composed of line segments. Think about our definition of polygons. Think about all the figures we can make that would satisfy the given, right? Make sure the given's true. And it turns out that this is actually a true conditional, right? By the definition of polygon, polygons are composed of line segments. Now, not there. There's more to the definition, yes, but this is a true statement. If I were to give you a polygon, it would be composed of line segments. So that's actually a true conditional. There are no counterexamples that I could find that would make this false. Let's do one more. No two primes have a difference of 2. Which I'm saying is pick any two primes and subtract them. You'll never find a difference of 2. This is actually false. Okay, that's a false statement. Because I can think of actually several examples where if I pick two prime numbers, the difference is 2. For example, 3, 5. Subtract those two, you get a difference of 2. 5 and 7. Those subtracted, get a difference of 2. 11 and 13. Subtract those, you get a difference of 2. I can keep going. 17 and 19. But all I need is one counterexample. So any set of two primes in which the difference is 2, well then I know that my statement above has to be false. All right, that comes to the end of our 2.1 lesson on conditional statements. Be sure to look at the worksheet there. There's more information to find on that. If you do have any questions on the worksheet, please do not hesitate to email me. And with that, be good and do good.